So let's get into the bonds that happen here, the bonds we can make. There's actually two categories, and one of them has two subcategories. Let's talk about ionic bonds. And our key word here is transfer. So keep in mind, if you transfer money with the bank, one of you gains it, one of you loses it. Here's we're going to be transferring electrons. And so one gains electrons, one loses it. So if I gain an electron, that makes a negative charge. If I lose an electron, that makes a positive charge. Easy enough. Sounds backwards. Sounds backwards. Keep in mind, electrons have a negative charge. All right. So we have names for these. What's this word ion? So an ion is an atom with a charge. Atom with a charge. All right. They come in two flavors. Anion, a negative. It's got an extra N for negative. N for negative. A negative ion. It's right there in the name. All right. Anion, that's our negative. And then we have this cation. All right. Now, I learned this all kinds of crazy ways, but let's just show you the easiest one here. Man, I wish I'd known this when I was a student. You see a positive, turn that T into a positive ion. You see a positive ion. Positive ion. All right. Easy enough. So we've got ionic. We'll get a plus, an atom that has a plus, and we'll get an atom that has a minus, and then they're opposites, and so these attract, and that forms our ionic bond. Is the attraction forces between these. All right. Okay. So ionic, then we're transferring. The next ones then we have to worry about are called covalent. And they come in two flavors. But here's my key word for covalent. They share electrons. All right, now our two flavors here, we've got nonpolar covalent. All right, so let's translate that. This is equal sharing. Both of them want it the same. They share it equally. All right. And then we've got polar covalent. Or unequal sharing. So we can use language on polar covalent that one of them has the electron longer or more often. You can also say the electrons are closer to it. Both are actually correct. All right, it's kind of going on at the same time. So unequal sharing and equal sharing. Now, here's where the confusion lies. In these chapters, the books will refer to ionic versus covalent, and they're talking transfer versus sharing. And they spend a lot of time looking at that. And then later they get focused in on covalent, and they'll say covalent versus polar covalent. And so they're talking equal sharing versus unequal sharing. So what I do, this nonpolar covalent for equal sharing, instead of you just calling that covalent like many books do, when I want to talk about this specifically compared to the others, I'll say nonpolar covalent. If I just say covalent, it's including both of these. All right. So when we share these electrons, most people are introduced this with the model of here's my nucleus and it's got all these plus charges. Here's my nucleus. And here's another nucleus and it's got positive charges. And if I put the electrons in the middle and they're negative, then they tie these nuclei together and they hold them together. It's not, I mean, it's a great picture. It gets the light bulbs on. It's a great idea to kind of think about it. We'll draw a lot of our stuff based off of that model. Not at all. What's really happening, really, the electrons kind of being split around, they orbit around both of them. We're going to look at, they just hold them together, okay? Now, we want you to know in these terms, easy enough, but we got to be able to predict these. And to do that, we use electronegativity. And so remember, electronegativity was how much an atom wants. How much an atom wants an electron, both to keep the ones it has and to gain new ones. Now, if I go in the book, I can pull up tables on electronegativity, and we can do all kinds of this term. You'll see this term, difference in En. All right. So difference is then going to be our difference or change. And so it's going to be, usually we think in final minus initial. But we just subtract the two electronegativities. And what we find is fluorine is the highest at 4.0. And cesium way over here is the lowest at 0.9. Nope. 0.7. All right, so the biggest difference we could have is 3.3. The smallest difference we could have, if I pulled up one of those tables, you would see it, but it's actually even easier if I do hydrogen and hydrogen. So this is usually 2.1 and 2.1. They both exactly have the same electronegativity. And so I would predict that difference would be 0. So the way that, if you were to try and do it with these numbers, you would look at the difference in electronegativity, and the top of this would be 3.3, and the bottom would be 0, and they split it in a couple of places. And the problem is they keep changing these places because they're trying to match the data. And so what we find is the numbers I remember is 0.5 and down is non-polar covalent. These want the electrons the same and or close enough, and so they share close enough. If I go 1.9 and up, so including 1.9, this would be ionic, and then in the middle we'd have polar covalent. And not only do they move these numbers, but it's kind of a spectrum as we move across. And so this misses some. This gets some wrong and gets some, they keep changing the answer. It's hard to come up with something, that predicts everything doing that way. So if that's going to miss some, and you got to look at those numbers or memorize those numbers every time, then let's go with a different approach. And the approach I'm going to use is looking at my periodic table. So I'm going to sketch out my periodic table and kind of get an idea of where things are. So I've got all these things. If I looked at a list, hydrogen at 2.1 does not fit anywhere over here. It actually fits over here. And that's our first kind of thing that I'm going to write down. So first thing I'm going to do is I'm going to say move, pin's trying to down me, move hydrogen above the B and the C. In other words, it goes right above this line, above the boron and carbon. So right in here, that's where my hydrogen is going to be. All right, now I can look at where things are. So I've got my staircase. If I cross the staircase, so if I go across the staircase, typically they use language like a non-metal and a metal. But if I cross my staircase, then it's going to be ionic. They're going to be far apart. And so the thing over here will be closest to cesium. It'll have the lowest electronegativity. The one over here, my non-metal, will be closest to fluorine, have the higher electronegativity. Keep in mind, the atom that wants it the most gets it. And so the one that's over here closer to fluorine will be my negative, and the one over here will be my positive. So we're now then going to say, so there's this, that's number 1. Here's number 2. So we cross the staircase. And that tells me it's ionic. Now remember, I had to move that hydrogen over. It's above the carbon now. So hydrogen and oxygen are not crossing that staircase. Okay. So then the next thing we're going to look at is when we don't cross the staircase, what do we have going on? So if I look at where they're not touching, so they're not touching, and touching, I mean side to side and up and down. Don't count corners. Side to side, up and down. So if they're not touching, but we don't cross the staircase. In other words, they're close, but not touching. So not touching. When we say touching, don't count the corners. All right. So they're not touching. Don't cross the staircase. They're going to have similar electronegativities, but they're different enough that they don't share equally. In other words, these are polar covalent. A good example of this is our hydrogen and oxygen. Hydrogen is up here, and now you can see it's not touching the oxygen, so we don't have to cross the staircase though, and so these would be polar covalent. And the one that is closest to fluorine then gets the electrons more. And so that's going to be the one that has more of a negative charge. It's not an ionic charge. It just has it more. We have a term for that, a partial charge. All right. Now, our last case then is what if they are touching, like nitrogen and oxygen? They touching side to side. So touching is our last case here. If the boxes are touching, that's going to be nonpolar covalent. You have to be careful in many of these questions they ask, is the bond polar or nonpolar? And so you have to be careful. If they're touching, then no, they're not polar. They're nonpolar, right? If they're not touching, then yes, they're polar. You got to be careful. That language shows up in lab a couple of times. So this is how we can use our electronegativity to tell what kind of bonds things will make. Okay, this is going to be very helpful in when we go to name things. It's going to be really helpful when we go to do talking about the properties and predicting everything all the way up until we start looking at melting points and boiling points, all kinds of properties. We can tell by just saying what kind of bond do we predict things to make. So we'll come back and we'll revisit this some more later, but we'll go ahead and end this one here. And just don't forget to move that hydrogen. You cross the staircase, it's ionic, which means a transfer. The one that's closest to cesium will be the one that loses the electrons. That's your positive charge, your cation. The one that is closest to fluorine will gain the electrons. It wants the electrons more, so it gains them. And that makes your negative charge your anion. Okay. Then when you get down here, we don't have those terms anion and cation. And so if we're not crossing that staircase, they're either going to be touching or they're not touching. If they're not touching, they're polar covalent. Unequal sharing. That idea of polar, that comes from a magnet, and you can draw a line and separate the north side and the south side. So when I have something like a hydrogen oxygen bond, the hydrogen is further away from fluorine. So we use this little symbol here, a partial negative and a partial positive. And we can draw a line to separate the positive from the negative sign. Now, when they are touching, it's nonpolar covalent. There's none of these charges. They're sharing perfectly equal.